What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 5, Section 6, Rational Functions. Let's do it. What is the fundamental difference in the algebraic representation of a polynomial function and a rational function? So in this case, a polynomial function is going to be like x squared minus 2x plus 3, something like that, right? And to make it into a rational function, now we're talking about this over essentially another polynomial. Let's say x cubed minus 2x squared plus 7. So that's just an example. There's the fundamental difference. Boom, done. If the graph of a rational function has a removable discontinuity, aka a hole, what must be true about true of the functional rule? So what this usually means, the way to identify it algebraically is you're going to have something that cancels out a factor. So let me give you an example. Let's say we have x squared minus 4x, let's make it minus 4x plus 3. And on the bottom, we have x squared minus 10x plus 21. So if we factor both of these, you're going to see that this will have a hole, aka a removable discontinuity, and I'll show you how to identify it. The top factors to x minus 3 times x minus 1. The bottom factors to x minus 3 times x minus 7. So these are going to cancel out. And this is the indication that, because we can cancel out a factor on the bottom and the top, that means we have a removable discontinuity, aka a hole at x equals 3. Now, where the position of the hole occurs is going to be found by taking this 3 value and plugging it into the simplified version, right? So after we cancel out the factors, it'd be 3 minus 1, which is 2 over 3 minus 4. Sorry, 3 minus 7 on the bottom, which is negative 4, which simplifies to negative 1/2. So the actual hole will be right at this point at 3 comma negative 1/2. So there you go. Can a graph of a rational function have no x-intercepts? And I would say absolutely yes. And we can even look at an example of a rational function that might have no x-intercepts, right? Something like this. I'm just going to kind of make it up here. But what it might look like is maybe we have something like going like this way, and then in the horizontal asymptote is the x-intercept, and then in here maybe it's going up. I'm just again making this up, and then here it's going down. So that's a graphical representation of how we might have no x-intercepts. And then in reality, if we're talking algebraically, what it would be is, usually we find the x-intercepts with the polynomial on top, that numerator. So let's say that numerator is going to have only imaginary roots. So if the numerator only has imaginary roots, then this would have no x-intercepts, right? Or alternatively, if there is a root on top, if there is like we saw in the last example, x minus 3 on top, but you also have that x minus 3 on the bottom, okay, in this case, that would cancel out to be a hole. So where you might have an x-intercept of 3, 3, 0, if it's a hole and you cancel it out, it will no longer have an x-intercept. So it might look like it goes through, potentially might go through here. But if you have a hole there, then it's not really an actual x-intercept. For this question, we're meant to find the domain of this function. And really, when we think about domain, we're really thinking about where can it not go? What are the domain restrictions? And there are two ways that you can have a domain restriction. The first way is if any value of x is going to make you divide by 0. That's out. We're not including that as our, as a real outcome, right? So, and the other one would be if you take the square root of a negative. That would, again, be an imaginary number. It wouldn't be a real number, so that'd be outside of the domain as well. Well, there's no radicals in this, so we don't have to worry about that. But we do have a denominator, and we're trying to see if and when that can ever go to 0. And we can figure this out by factoring that denominator. It's a difference of squares, x minus 1, x plus 1. When is that going to equal 0? That's going to equal 0 when x equals 1, or when x equals negative 1. It's going to 0 out. And that means that these are the restricted values, meaning x cannot equal 1 or negative 1, those points where it zeroes out. So we can say now that the domain is every number except for 1 and negative 1. All real numbers except for 1 and negative 1. Boom, done. For this one, right off the bat, we have to look at when the denominator goes to 0, because we're talking about domain. We're really talking about what are the restrictions of the domain, and we're not allowed to divide by 0. So anything that's going to make us divide by 0, it's out. So we're really concerned with factoring the denominator, not the numerator. So I'm going to leave the numerator as is, and then we're going to factor this guy. So that we can kind of treat it like a quadratic. It's just, higher degrees, x to the fourth instead of x squared instead of x. So in here, I'm going to put x to the squared x squared, because that multiplies to x to the fourth. Then what two numbers multiply to 4 add to -5? That's -1 and -4. And then we can factor these further, right? So I can factor that denominator a little bit more. And we've got, again, difference of squares, x minus 1, x plus 1. And then over here, x minus 2, x plus 2. And what's going to send this denominator to 0? It's going to be when x equals 1, when x equals -1 for this guy. For this one, it's when x equals 2. And for this one, it's when x equals -2. But the real thing is, the domain is when this is not true, aka x cannot equal 1, -1, 2, -2. So it's all real numbers except x cannot equal these 4 values. There you go, boom, done. So for this one, we're first meant to find the vertical asymptote, horizontal asymptote, and the domain. Okay, so I'm going to put those 3 things here. Now, when we talk about the vertical asymptote, it's what's going to make this denominator go to 0. That's going to be our vertical asymptote. And we have to make sure that it doesn't cancel out, right? There's no canceling. If it cancels, then it's not a vertical asymptote. We're talking about a whole. But here, there's nothing to cancel. We just got a 2 on the top. So when is this going to go to 0? When is 5x plus 2 going to equal 0? Well, we just solve for x now. 5x equals -2. Subtract 2 from both sides and then divide by 5. X equals -2/5. So this is what's going to send it to 0. And that is our vertical asymptote. X equals -2/5. And again, that's a vertical line. X equals -2/5 goes up and down. And that's our vertical asymptote. By the way, this also tells us our domain. This is the one spot where x cannot go. So x is all reals except for this -2/5. And then last but not least, we want this horizontal asymptote. So there's a nice little rule here. When the degree on the bottom, which is 1, is greater than the degree on top, which is 0, right? 2 times x to the 0. X to the 0 is 1, is a way to think about it. But it's just a constant. When the degree on the bottom is greater than the degree on top, then we know the horizontal asymptote is going to be right on that x-axis, aka y equals 0. So now we got vertical asymptote, horizontal asymptote, domain, boom, done. So for this one, we're finding the vertical asymptote, the horizontal asymptote, and potentially then the domain after that. So I'm going to start with the vertical asymptote. The vertical asymptote is going to occur wherever the x values are going to 0 out in the denominator. So first, I'm going to factor that denominator. And we've got what two numbers multiply to -36 and add to +5. That would be +9 and -4, okay? So what values are going to 0 this out? It's going to be -9 and +4. So my vertical asymptotes are x equals -9, a vertical line there, and x equals +4, a vertical line there. That also is going to contribute to my domain, because my domain is all reals except when x equals -9 and 4. So x just cannot equal -9 and x cannot equal 4. Now we get to the horizontal asymptote. As long as the degree on the bottom is bigger than the degree on the top, which it is here, we know that the horizontal asymptote is by default in that situation y equals 0, aka the x-axis. So there are your answers. Boom, done. So for this one, we're meant to find the vertical asymptotes, the horizontal asymptotes, and then the domain. So we're going to start with the vertical asymptote, and that's going to be when the denominator is going to go to 0. So we're going to factor that. First, I see it's got a GCF of x, so I'm going to pull that out, and we've got x squared minus 16 left inside. And then this is a difference of squares, so let's factor that more. X minus 4, x plus 4. All right, now we have 3 different spots where this thing is going to 0 out, right? And by the way, we do have to check with the numerator. If the numerator is factorable and something cancels out, then it's no longer a vertical asymptote. But we don't have that situation here, so we don't have to worry about the numerator. And where is it going to 0 out? When x equals 0, right? That's going to 0 the whole thing out. When x equals 4, that's going to 0 this out. And then when x equals -4, so we got there are 3 vertical asymptotes. Then for the domain is based directly off of these vertical asymptotes. These are places where the domain does not exist. So the domain is all reals except x does not equal 0, -4, and 4. And last but not least, when we talk about the horizontal asymptote, since once again, the degree is larger than the numerator degree, right? That's 1, that's the highest degree is 3 there. then we know that the horizontal asymptote is going to be y equals 0. Boom, done. For this one, we want to find the vertical asymptotes, the horizontal asymptotes, and the domain at the end. So once again, we're going to start by what's going to zero out the denominator. So I'm going to factor that denominator, but this time I'm going to keep the numerator here as well, and you're going to see why. So that's a difference of squares, and it factors to x plus 5, x minus 5. So the interesting thing here is that we actually have a cancellation happening. Now, when you cancel out a binomial like this, that means that you're actually going to have a hole at x equals -5, what would have otherwise been a vertical asymptote. So that cancels out and it simplifies to 1 over x minus 5. So that hole is not a vertical asymptote, of course. So this is the remaining denominator. That's where we find the vertical asymptote, where this zeroes out, which is at x equals 5. Now we're talking about the horizontal asymptote again, even in the beginning, but before we simplified, but also in the simplified version. Either way, the degree on the bottom is bigger than on top, right? That's 1, that's 0. Here it's 2 versus 1. Either way, that gives us a horizontal asymptote of 0. And last but not least, our domain is going to be all reals except x does not equal 5. That's our vertical asymptote. But don't forget about that -5. There's also going to be a hole at -5. So it's all reals except for that hole and that vertical asymptote. Boom, done. So for this one, we're finding the vertical asymptote, the horizontal asymptote, and the domain. So we're going to start with that vertical asymptote, and that's going to be when the denominator equals 0. And by the way, you got to be careful that whatever you get here, as long as if you can cancel it out, right? If you got 3x minus 1 on the top and the bottom, and they cancel out, then that's no longer going to create a vertical asymptote. But there's nothing like that happening here. So when is this going to equal 0? It's when, as we add 1 to the other side and divide by 3, it's when x equals 1/3. That's what's going to zero this out, and that's our nice vertical asymptote, x equals 1/3. This leads us into the domain, which is all real numbers except for that positive, 1/3. So all reals and x except for 1/3. X does not equal 1/3. Now we get to the horizontal asymptote. So now if you look, the degrees are actually the same in the numerator and the denominator. So when that's the case, we take those leading terms, which is -2x over on the bottom positive 3x. The x's cancel out, and we're left with a ratio of those coefficients of -2/3. And that's what's going to be our horizontal asymptote. Y equals -2/3. Boom, done. Here we're trying to find the x and y intercepts for this function. So x-intercepts are, of course, when the function value goes to 0, and the y-intercept is when the x value is at 0. So the thing is, if we start with the y-intercept, if you actually plug in 0, you get 0 over 0 minus 0, which is 0, right? 0 squared is 0, minus 0 is 0. That's indeterminate. That means there is no y-intercept. And just as a reminder, it's indeterminate because you can't divide by 0. Now, what about the x-intercept? When is this function going to actually go to 0? Well, typically that's when we make this numerator go to 0 in and of itself. But the problem is the only way to make the numerator go to 0 is to also simultaneously make that denominator go to 0, right? 0 over 0 minus 0. And again, that's indeterminate, which means there's no x-intercept either. So there's no x or y intercepts. Boom, done. So for this one, as we start, we've got, again, x-intercepts and y-intercept. And there's only going to be one at most y-intercept. And we can start with the y-intercept because in this one, it's when x equals 0. So we can just plug and chug and see what we get. 0 plus 0 plus 6 over 0 minus 0 plus 24. And as you reduce that, 6 over 24 is the same as 1/4. So we got a y-intercept at 0, 1/4. What about the x-intercept? That's where we're going to zero out the function value. And really what we care about is zeroing out the numerator, so long as we don't also simultaneously zero out the denominator. So just to be safe, I'm going to factor the numerator and the denominator. So on top, what multiplies to 6 and adds to 1? Actually, that's not factorable because there's no two numbers that multiply to positive 6 and add to positive 1. The denominator is factorable, so we'll factor that. It's going to be x minus 6, x minus 4, because the two numbers that multiply to positive 24 and add to negative 10 are negative 6 and negative 4. So since this isn't factorable, there's definitely not going to be anything that's going to cross out. We're going to have to run it through the quadratic formula to find out when this is going to go to 0. So we've got a, b, and c. We got negative b, which is negative 1. That's the coefficient in front of x, plus or minus the square root of b squared. That's 1 squared, which is 1, minus 4 A is 1, right? 1 is that coefficient. And then C is 6 over 2 times A, which is 2 times 1, which is just 2. Now you can already see that I'm going to get 4 times 6, which is 24. 1 minus 24 is going to be negative 23, which means that the outcome of this is going to be two imaginary numbers, two complex numbers with an imaginary component. That means there's no real x-intercepts. It's not going to be an actual real number x-intercept. So there's only a y-intercept at 0, 1/4, boom, done. So for this question, we're meant to describe the local behavior as well as the end behavior. And when we're talking about local behavior, we're talking about behavior around any vertical asymptotes, if there are any. So let's first get that vertical asymptote. That's going to be when the numerator goes to 0. So when does 2x plus 1 equal 0? When x equals, I'm going to subtract 1 from both sides, divide by 2, right? Well, all I'm doing is I'm isolating x. So it's when x equals negative 1/2. So that is my vertical asymptote. Vertical asymptote is x equals negative 1/2. So what we're thinking about is we're looking at trying to, what's happening as x approaches negative 1/2 from the left and from the right, right? So we can sort of see from the left as x approaches negative 1/2 from the left, right? We put that little minus sign up there to indicate, hey, we're coming from the left-hand side. We can imagine values less than negative 1/2, like negative 1. So you plug in negative 1, you get negative 1 over negative 2 plus 1, which is negative 1, so we get 1. Now let's get a little bit closer to negative 1/2. We'd plug in negative 3/4, for example, right? So we'd get negative 3/4 over 2 times negative 3/4 is negative 3/2 plus 1. This gives me negative 3/4 over negative 3/2 plus 1 is negative 1/2. So it's basically like negative 3/4 times negative 2, which is 1.5, okay, or 3/2. So you can see that as we're getting closer and closer to negative 1/2, we seem to be going up. Now you could try, like negative, well, what did we say? Negative 1/2. So you could try like negative 0.51, stuff like that. You could plug it into a calculator. You see it's going to go up and up and up, okay? So on this vertical asymptote, it appears that as we approach from the left, the function value is approaching positive infinity. Now, what about as we approach this negative 1/2 from the right? Okay, so now we can try values on the other side of negative 1/2, maybe like 0. For example, here we'd have 0 over 0 plus 1, which is 0. So you have that coordinate of 0, 0. Let's try negative 1/3. Okay, that's a little bit tiny bit bigger than negative 1/2. So let's plug that in. Let's see what we get. So you plug in negative 1/3, you get negative 1/3 over negative 2/3 plus 1, which is 1/3. That simplifies to negative 1. So it sure appears like it's going down. Now again, you could try something like 0.49, right? Just to the right. And we could do that. Let's do that just for fun. Negative 0.49 over 2 times that is negative 0.98 plus 1, which is positive 0.02, something like that, right? And then you divide by that, you're going to move the decimal over twice as we move this over twice. So it's like negative 49 divided by 2. It is, hold on, let me write this out here, negative 0.49. And then you're getting, what is that, negative 24.5, right? So that clearly shows you we're really increasing fast. We're really approaching that negative infinity. So as x approaches negative infinity from the right, the function value is approaching negative infinity. All right, so there's the local behavior. Now when we're talking about end behavior, we're again thinking about that horizontal asymptote, which you can kind of shortcut here. You can look at both these leading terms here, and they both have the same degree. So when they have the same degree, that horizontal asymptote is going to be the ratio or the fraction of those two coefficients, which is 1/2, right? So the horizontal asymptote is y equals 1/2. And what that really means is as x approaches infinity, both positive and negative, but as we go to the right and as we go to the left, the end behavior is going to be the same, which is the function value is approaching this horizontal asymptote, which is 1/2. There you go. Boom, done. So for this one, we're trying to find the local and end behavior. The local behavior is going to occur around wherever our vertical asymptote is. And since we have x minus 6, this thing is going to zero out when x equals 6. So that's the vertical asymptote. So we've got two possibilities, right? What's happening as x approaches 6 from the left, and what's happening as x approaches 6 from the right. So let's flesh that out a little bit. So 6 from the left, we're thinking just smaller than 6, maybe like, 5, 5.5, et cetera, et cetera. So as we're getting closer and closer. So let's check out 5 first of all. So if we plug in 5, we get negative 10 over negative 1, right? 5 minus 6 is negative 1, which is positive 10. What about 5.5? Let's see, we get negative 11 over negative 0.5. Dividing by negative 0.5 is like multiplying by negative 2. So that's 22. So you can see with those two quick examples, we definitely seem to be getting bigger and bigger, which means that the function value as x approaches from the left is approaching positive infinity. It's probably approaching negative infinity from the right, but let's test it out just to be safe. So we're going to try two values. We're going to try 7 first, and then we're going to try 6.5. When we try 7, we get negative 14 over 7 minus 6, which is 1, so that's negative 14. When we plug in 6.5, we get negative 13 on top over 6.5 minus 6, which is 0.5, divided by 0.5 is like multiplying by 2, that's negative 26. So it sure seems to be approaching negative infinity, which is what we kind of predicted. Last but not least, when we look at our end behavior, okay, we're really talking about the horizontal asymptote. And since the degree on top and bottom is the same, the horizontal asymptote is y equals the ratio of the numerator over the denominator coefficient. So negative 2 over 1, which is negative 2. And since that's a horizontal asymptote, that is also the end behavior as x approaches positive and negative infinity, meaning as we go really far to the right and really far to the left of the graph, the function value in both cases is approaching negative 2. Boom, done. For this one, we're going to start by factoring both the numerator and the denominator. So if I factor the numerator, first I'm going to pull out a GCF of 2, which leaves x squared minus 16. And then I can further factor this as a difference of squares. So a difference of squares would be x and x here, and then the square root of 16, which is 4 and 4 there. And then we mix it up with a plus and minus. Now let's factor the denominator, but we got a leading coefficient. So we're going to use the nice star method where we've got a, b, and c. And a goes here and here. A times c, 6 times negative 5, which is negative 30, goes up top. And then b, 13, goes down here. So what two numbers multiply to negative 30 add to positive 13? That would be 15 and negative 2. This reduces to 3 over negative 1. This reduces to 2 over 5. And circle both of those because this is the coefficient of the x. That's the constant, same here. That same breakdown, top, bottom. So we've got 2x plus 5, and we've got 3x minus 1. So I factored the numerator and the denominator just to double check that, do we have a local discontinuity or do we have a vertical asymptote, something like that. So whether or not we have a removable discontinuity or a vertical asymptote. So since nothing's canceled out, both of these represent vertical asymptotes. So we got a vertical asymptote at x equals whatever zeros this out, which is negative 5 over 2, and whatever zeros this out, which is positive 1/3. So now we got a lot of work to do. So what happens as x approaches negative 5/2 from the left? So now as you plug in values that approach negative 5/2 from the left, let's say like negative 4, then negative 3, as we're inching closer and closer, what you're going to see is that the function values are going to get more and more negative, meaning we're approaching negative infinity. And again, you can plug this in using a calculator with those values I mentioned and just plot it out. Conversely, when we have x approaching negative 5/2 from the right, okay, as the values are getting closer to that, so that's negative 2.5. So imagine negative 1, then negative 2. What you'll see is the function values are actually getting closer and closer to positive infinity. They're getting bigger and bigger. So that's the local behavior around that asymptote. What about the other asymptote? What about 1/3 from the left? So as you plug in values from the left, right, we're talking maybe 0, maybe 1/4 as we're inching up there, right? The function values are actually going to get bigger and bigger that you can verify in a calculator. So as we approach it from the left, we're getting positive infinity. And then you can do the same thing as you approach 1/3 from the right. Maybe you can plug in 2, then 1, and so on and so forth. And what you'll see in that trend is the function values are actually getting smaller into the negatives, aka approaching negative infinity. Last but not least, we need to address the end behavior. And again, we can do that by finding this nice horizontal asymptote. Since the degrees are equal for the numerator and the denominator, the horizontal asymptote is the ratio of 2/6, which reduces to 1/3. So there's my horizontal asymptote. And what that means is here, let's do it like this. X approaches either positive or negative infinity, right? As we go really far to the right and really far to the left, the function value is going to be approaching this horizontal asymptote, which is a value of 1/3. So there's your answer, done. For this one, we're meant to find the slant asymptote. And now the giveaway that there is even in an actual slant asymptote is that the numerator degree is greater than the denominator degree. Now, to find that slant asymptote, we go back to our nice polynomial long division. So let's do that now. We'll set it up, 2x minus 4. And again, we're only concerned with that leading term, right? So how many times does 2x go into 4x squared? Or what do I multiply this by to get this? That would be 2x. So we're just going to put a 2x up here. Usually I'd put that over the x term, but there isn't one, so we'll just kind of leave it there for now. Doesn't really matter. 2x times 2x is 4x squared, and then also multiply against that negative 4, the entire binomial, and we get negative 8x. So then we're going to subtract the bottom, aka negate, and add. It's the same idea. Those cancel out. There is no 8x, so the 8x just drops down, and that negative 10 comes down with it. And then once again, 2x goes into 8x how many times? 4 times. So we have plus 4. 4 times 2x is 8x. And then times negative 4 is negative 16. Negate. That cancels out when you add. And when these guys add, you have a remainder of 6. But the beauty of the slant asymptote is we don't really care about the remainder. The slant asymptote is what we've got up here for the quotient, which is y equals 2x plus 4. Boom, done. For this one, I just want to start by saying that we do know that there's indeed a slant asymptote because the degree here on top is higher than on bottom. So that's how we even know there is a slant asymptote. Now to find it, we're going to go ahead and carry out some nice long division polynomial style. So we're just looking at these leading terms here, meaning what times 3x squared gives us 6x cubed? That would be positive 2x. 2x times 3x squared gives us that nice 6x cubed. 2x times 4 gives us a positive 8x. Now we negate, and these guys cancel out as we add them together. Negative 5x plus negative 8x is negative 13x. Well, look at this. The degree here is already below this. So that means we're done. We're at our remainder. But the thing is, we don't really care about the remainder when we're talking about slant asymptote. We just care about that nice quotient at the top. So the slant asymptote is y equals the quotient 2x. Boom, done. So this one says the reciprocal function shifted up 2 units. So what is the reciprocal function? The reciprocal function is 1 over x. So just so you can kind of see, it's got a nice vertical asymptote at 0, a nice horizontal asymptote at y equals 0, and it typically looks like this. It goes blop and blop like that, right? Not actually touching those asymptotes. So let me move it over just to make it more precise. Now, when it says it shifted up 2 units, it goes up and up like this. That's literally what's happening. So now that new horizontal asymptote is no longer going to be the x-axis or 0. It's going to be y equals 2. But the vertical asymptote is not going to change. So the vertical asymptote is still going to be at x equals 0, but the new horizontal asymptote is going to be now at y equals 2. And now we're going to take a look at the graph on Desmos. So here, once again, we've got the reciprocal function 1 over x shifted up by 2, so plus 2, and you can see that nice horizontal asymptote occurring here at y equals 2, and that vertical asymptote at x equals 0. Boom, done. Now we're talking about the reciprocal squared function. That's 1 over x squared. And typically what that looks like is we've got a nice vertical asymptote at x equals 0 and a nice horizontal asymptote at y equals 0. And then it goes up both ways, right? When both sides approaching that vertical asymptote, it's going up, going towards positive infinity. So now what does it say? It said it's shifted to the right 2 units. So you can see that this horizontal asymptote is not going to get affected, but shifted 2 units right, it's going to kind of go like this, okay? And let's move those arrows as well. So now that new vertical asymptote is no longer going to be at x equals 0. It's going to be at x equals 2. So we got vertical asymptote x equals 2. Horizontal asymptote stays as is at y equals 0. And now let's look at the graph in Desmos. To indicate a shift 2 units to the right, we need to put parentheses around that x and subtract 2 like so. And you see now we've shifted 2 to the right. So you can see that vertical asymptote is at x equals 2. The horizontal asymptote still y equals 0. That's how you do it. Done. So for this question, we're meant to find the asymptotes as well as the x and y intercepts. So let's begin. So first we're going to start with the vertical asymptote. That's when we're going to zero out the denominator, and that's going to be when x equals -4. Next, we find the horizontal asymptote. Since the degrees on the top and bottom are the same, the horizontal asymptote is going to be the ratio of those coefficients of the leading terms, which is y equals 2 over 1, which is simply 2. Now, when we're trying to find the x-intercepts, or sept in this case, it's where does the numerator zero out? So as long as we don't also zero out the denominator, but there's nothing in common in terms of factors or binomials that it can cancel out. So what's going to make this top go to 0 when x is 3 over 2? Because 3 over 2 times 2 is 3, minus 3 is 0. So we got an x-intercept at 3 over 2, or 3 halves, comma 0. And then our y-intercept is going to be when x is 0. So we can plug in 0 for x. That's -3 over +4 as these zero out. So we've got 0, comma, -3/4. So now as we're graphing this out, I start with the vertical and horizontal asymptotes as dotted lines. So here is x equals -4, that nice vertical line. And then we have y equals 2, which is a nice horizontal line, hence the horizontal asymptote. And then we can plot the x-intercept, which is 3 halves and comma 0, which is like 1.5 right here. And then the y-intercept 0, -3/4, which is approximately right here. So this kind of gives us enough to begin to sketch this graph out, because I know that in this side, we're obviously below that horizontal asymptote. So what that tells me is we're going to kind of continue on out and then hug that asymptote as we continue out. Likewise, as we come to the left, boom, there's another asymptote that's going to block it, but it's going to hug it and it's going to curve down. Now the question is, on the left side, is it either going to look like this or like this? It's one of the two. And a quick way to check that is, look, this is at -4. Why don't we plot -5 and see, are we above or below? So if I plug in -5, I get -10 minus 3 is -13. Over -5 plus 4 is -1. We get +13. It's way up here. So what does that tell me? It means that we're definitely above this. Just for fun, let me plug in something where I know we can actually plot it. We can get an actual value. Let me try -8, for example. If I plug in -8, so just for illustration purposes, I'm going to plug in -6 up here, and we're going to get an actual concrete point to plot, just so we get some frame of reference. So you plug in -6, you get -12 minus 3 is -15. Over -6 plus 4 is -2. Negatives cancel out, that becomes 7.5. So -6 and then 7.5 is like right up here, just so you can see. And then, like I said, you could plot more points if you want to check it, but basically it's going to go up, and then here it's going to come down, and it's going to approach but never cross this horizontal asymptote. So that's a reasonable graph. Boom, done. So for this one, we're going to start with the vertical asymptote. So the vertical asymptotes are where we zero out in the denominator, which is going to be at x equals 2. Now, it does have this interesting exponent here, which gives it a multiplicity of 2, but we're going to talk about why that matters in a little bit. Next, we have a horizontal asymptote, and since the degree is bigger on the bottom than at the top, it's nice and simple. The horizontal is y equals 0. Now, if we're trying to find an x-intercept, if there is indeed one, it would be when we zero out the numerator. But that's a constant. We can't zero it out. So no x-intercepts, we'll just say none. And then for the y-intercept is nice because the y-intercept exists when x equals 0. So plug and chug. 0 in for x. 0 minus 2 is -2. Squared is +4. So that's 4 over 4, which is 1. Now we're going to start with the asymptote. So first I have a vertical asymptote at x equals 2, which is this nice vertical line here. Then I have a horizontal asymptote at y equals 0, aka the x-axis. No x-intercepts, which makes sense because if I have an asymptote there, I'm not touching the x-axis. And then I've got a y-intercept at 0, 1. So this y-intercept is enough for me to be confident that this function is going to kind of go like this. This is just roughly, and you're welcome to plot more points to make it more accurate, but I feel pretty confident that that's a great representation, hugging the asymptotes on both sides. Now the second question is is on the right side, is it going to look like this or like this? Now, because this asymptote has an even multiplicity, it means we're going to see a mirroring, meaning we're going to see something like this. But don't just take my word for it. Instead, what you can always do, even if you're like, man, I'm just not totally sure about that multiplicity rule, just plug in a point. You can always do that. You can always check and then be certain. So for example, this is occurring at x equals 2. What about 3? If we're above the asymptote, we know it's like this. So let's plug in 3. We got 4 over 3 minus 1 is 1 squared is just 1. So check that out. We got 3 comma 4. So there's our nice point. So look at that. That verifies that we are indeed above like this. This is just an approximation. But there's your graph, boom, done. For this one, we got a pretty complicated numerator and denominator. So I'm going to start by factoring both. We're going to have to use star method because they both have a leading coefficient. And remember, we got A, B, and C. I got A up here and here. So since my A on the numerator is 3, we got 3 here and here. We got A times C, which is negative 15 up top, and that negative 14 B term on the bottom. What two numbers multiply to this and add to this? That's going to be negative 15 and positive 1. And then I can reduce this one to be 1 over 5, right? Divide top and bottom by 3, just like a fraction. So now we've got that and that. So that means the numerator factors to 1x minus 5 times 3x plus 1, right? That goes with the x, that goes with the constant, that goes with the x, that goes with the constant. For the denominator, we're going to run the star method one more time. Again, we've got A is 3, that goes here and here. We got A times C, which is negative 48, that goes up top, and then B, 8, goes on the bottom. What two numbers multiply to negative 48, add to positive 8, so we've got positive 12 and negative 4, and this reduces like a fraction to 1 over 4. So there's that and there's that, which means we've got 1x plus 4, and on the other side, 3x minus 4. So this is great. Now that we have it factored, we can do a lot. So let's start with our nice vertical asymptotes. And everywhere where the denominator zeroes out here, we're going to have a nice vertical asymptote because there's nothing that's canceling out. So we don't have to worry about a hole or something like that. So we got a vertical asymptote here when x equals negative 4. We also got one here when x equals positive 4/3, right? 4/3 times 3 is 4, minus 4 is 0. Now, what about the horizontal asymptote? So since we have equal degrees, okay, we've got a horizontal asymptote, and the horizontal asymptote will therefore then be at the ratio of those two leading coefficients, 3 over 3, which equals 1. There's a nice horizontal asymptote. Now we can find those nice x-intercepts, which are going to occur when the numerator zeroes out. So the x-intercepts are going to occur here when x equals 5. And also here when x equals negative 1/3. Last but not least, we want our y-intercept, aka when x is 0. So we're going to plug and chug, right? Plug 0 in, that goes away, and we got negative 5 on top over 0, 0 over negative 16. And that means we have a y-intercept of 0, 5 over 16. So once again, I'm going to start graphing by graphing the asymptotes. We got x equals negative 4, which is over here. Then we've got graphing x equals 4/3, which is 1 1/3, which is approximately right here. Then we got a horizontal asymptote at y equals 1. So there's our horizontal asymptote. And then we got a couple intercepts that we want to plot. So we got 5, 0. We've got negative 1/3, 0, which is like right here. And then we got 0, 5/16 for the y-intercept. And that's like less than half. Let's say somewhere up here. Okay. So now on the right-hand side, we're pretty definitive that we've got this really nice thing. We're underneath this curve. So I can say we're going to go up and as per usual, hug that asymptote here. We're going to go down and that's a nice approximation. What about to the left? Well, we don't have a point of reference. So again, maybe we can plug in negative 5. So as I plug in negative 5, I got negative 5 minus 5 is negative 10. Negative 5 times 3 is negative 15 plus 1 is negative 14 over negative 5 plus 4 is negative 1, and then negative 5 times 3 is negative 15, minus 4 is negative 19. And as we simplify that out, negative, 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 it's going to be positive. 10 times 14 is 140 over 1 times 19, which is 19. But, you know, this is around 7, right? 20 goes into 140 exactly 7 times. Bottom line is it's a high positive number. Let's say it's a little bit more than 7. So something right here. So this is enough information for me to conclude like this is going to go up and up and up, and then it's going to come down like this. And once again, hug that asymptote as we go to the left. Now we have the very interesting question of what's happening in the middle here. So I can see that this appears to be going up, right? And even though we have this horizontal asymptote, it's not definitive that this thing is just never going to hit it. Sometimes in the middle, we see crosses of the horizontal asymptote. So the way we want to check this is I want to plug in 1. And I want to see what happens if I plug 1 in, because 1 is right here. So we're going to see where that goes. So I'm going to plug it into the unfactored form just because I think it's a little bit faster. We got 3 minus 14, which is negative 11, minus 5 is negative 16, over 3 plus 8 is 11, minus 16 is negative 5. So those negatives cancel out. 16 over 5 is a little over 3, which means 1 is going to be somewhere up here. So I already know now as we go up to the right, approaching that asymptote from the left, we're going up and up and up. And now the question is it also going up? Are we crossing the asymptote again? Or are we heading down, right? So let's plug in, I don't know, negative 3. Let's see where we're at. So here, putting it into the unfactored form is going to be kind of tricky. So I'm going to plug it into the factored form. Negative 3 minus 5 is negative 8. Negative 3 times 3 is negative 9, plus 1 is negative 8. So we got positive 64 on top. Then we got negative 3 plus 4 is 1. Then we got negative 3 times 3 is negative 9, minus 4 is, negative 9, right? Yeah, minus 4 is negative 13. So it looks like we got a positive 64 over a negative 13. That's really close to negative 5. So somewhere around here, but maybe a little bit under negative 5, or like a little bit like higher than negative 5. So it doesn't really matter because this is enough information to see that we're going down, right? You could keep plotting points, but that's going to be where it's headed. So now we have our nice complete graph of the rational function. Boom, done. For this one, we're going to start by factoring both the numerator and the denominator. So for the numerator, what multiplies to negative 3 and adds to positive 2? That's going to be positive 3 and negative 1. And for that denominator, that's a difference of squares. So we got x minus 1 times x plus 1. Now, this is very important because you notice these guys are going to cancel out. So that's something to remember because that's what's going to create that removable discontinuity, aka a hole. So we got x plus 3 over x plus 1 that we're going to analyze further. But remembering that we have a hole or removable discontinuity at 1 comma something. And how do I figure out what the function value is of that hole? Well, I plug that 1 into the simplified version. So that's 1 plus 3 is 4 over 1 plus 1, which is 2. 4 over 2 simplifies to 2. So we have a hole at 1, 2, and I'm going to show you how to plot that in a little bit. Now let's talk about, this is our a sub a of x. Now let's talk about our vertical asymptote. Again, it's where this zeroes out in the denominator, no longer including the part before we did the canceling out. So it's just that x equals negative 1. What about for a horizontal asymptote? Since the degrees are the same, it's the ratio of the coefficients, aka y equals 1 over 1, which is 1. Last but not least, let's get those nice x-intercepts and y-intercepts. So the y-intercept is going to be when we plug in 0 to the x. So that's going to 0 out, 0 out. We got negative 3 over 0 minus 1, which is negative 1. Negative 3 over negative 1 is positive 3. And what about the x-intercepts? The x-intercepts is where the function goes to 0. And where's the function going to go to 0? It's when the numerator goes to 0, but after we cancel this out. So that's going to happen when x equals negative 3. So now we got enough information. Let's start by plotting these asymptotes. So a nice vertical asymptote at x equals negative 1. A nice horizontal asymptote at y equals 1. We got an x-intercept at negative 3 comma 0. A y-intercept at 0 comma 3. And then what about this hole? We have a hole at 1 comma 2. So the way we plot a hole is we say 1 comma 2 is right here. Now that's going to be on the path of the function, but we're putting a little open circle to indicate that even though it looks like it goes through that point, there's actually no value there. There's no function value there. It's not a real point. But this right here is enough information to plot because we have a point in this region and we have a point in this region. So we can kind of just follow along the asymptotes that we've done before, just sort of hug the asymptotes as we go up and as we go to the right. Likewise here, as we go to the right, we already know we're in this region, can't be up here as well. So we know that we're just going to hug that asymptote coming down. As we go to the left over here, we're going to hug that asymptote. And here, as we go to the left, we're going to hug that asymptote as well. And so there's the graph of the function. Boom, done. So for this one, we're going to once again start by factoring the numerator if it is indeed factorable. Since we got a leading coefficient, we're going to factor using the star method where we got a, b, and c. We got our a term up here. We got a times c, 2 times -1, which is -2 here. And then the b term of 1 here. So what two numbers multiply to -2 add to 1? That would be +2 and -1. That cancels out 2 over 2, just like a fraction, to 1 over 1. So now we have the components, which would be this. The top part goes with x, so 1x, and the bottom part is the constant, x plus 1. And then here we'd have 2x minus 1 over x minus 4. And there's nothing that cancels out, so there's not going to be a removable discontinuity. But this is going to be helpful to find the x-intercepts and so on. So now let's begin. First of all, the vertical asymptote is going to be when this zeroes out. So the vertical asymptote is going to be at x equals 4. Now the question is, what's the horizontal asymptote? Or really, is there a horizontal asymptote? Now, when the degree on top is greater than the degree on the bottom, this means that there's actually not going to be a horizontal asymptote, but a slant or oblique asymptote. And the way we find that is by doing good old-fashioned polynomial long division, dividing top by bottom. So as we start the polynomial division, we just look at the leading terms. How many times does x go into 2x squared? It goes in 2x times, meaning 2x times x gives us exactly that match of 2x squared. But then we also must multiply the -4, so we get -8x. Now we negate, meaning I flip both the signs and add them together. It's the same as subtracting. So that cancels out. 8x plus 8x is 9x, bring down that -1. Now what times x gives us that 9x? Again, looking just at the leading terms, that's going to be a +9. 9 times x is 9x. 9 times -4 is -36. So we negate. This part doesn't matter so much, and I'll explain why in a second. Then we get -1 plus 36, which is a remainder of 35. But this remainder doesn't factor into the slant asymptote. This quotient is the slant asymptote, which means our slant asymptote is y equals 2x plus 9. Now we need our x-intercepts as well as our y-intercepts. So the x-intercepts, there's actually going to be two. It's going to be the two places where we zero out the numerator to get a function value of 0. It's going to be at -1 comma 0. That's going to zero this out. And then we also have it +1/2 comma 0. And then for the y-intercept, we just plug 0 in for x. So that goes away, that goes away. We got -1 over -4. Which is +1/4. So we got 0 comma 1/4 for the y. So just so we have a little bit more room, I replaced the graph with larger numbers. So now this should make it a little bit easier to graph. So we have a vertical asymptote at x equals 4. So this is 5, 10, 15. You can see like that, right? So x equals 4, we're going to have a vertical line right about here. And then for our slant asymptote, we've got a y-intercept of 9, which is somewhere here, and then a slope of 2. So as we kind of map this out, we're going up 2 over 1. Now I know that we're in, a different scale where each one is 5, but it's still like going up 10 over 5, right? So it's still a slope of 2. And then we can sort of expand this out. So now we got a nice little representation. Now what about these intercepts? Let's plot those. So we got an x-intercept at -1, 0, which is approximately right here. And then we got another one at 1/2, 0, which let's say is right around here. And we also have a y-intercept of 1/4, like really, just approximating, but something like that on the y-axis. So we got a pretty good idea that this thing is on the inside. And then again, just like our typical graphs, we're following or hugging those asymptotes as we go down. We also know pretty likely that the other part of the function is going to be up here. But just to be safe, we can do a nice plug and chug. Why not plug in 5? It's just to the right of that vertical asymptote. So when I plug in 5, I got 5 plus 1 is 6, times 2 times 5 is 10, minus 1 is 9, over 5 minus 4, which is 1. So that's 54 divided by 1 is 54. So it's really, really way up there. But, this isn't going to be the most accurate positioning, but let's just say roughly it's going to look like this. And again, following that same behavior up top, it's going to hug that asymptote there. So there's a representative graph, boom, done. So for this one, we've got it in fully factored form, which is really nice, and nothing cancels out. So we're good to go in finding the vertical asymptotes, which is going to be where the denominator zeroes out. So it's going to be at x equals -2 and x equals 4. In terms of the horizontal asymptote, if there is one, we got to look at the degree of the numerator and the denominator. So since I have x, I know my highest degree is going to be x cubed, and the coefficient's actually going to be 1. For the bottom, since I have this one squared and then another x, it's again going to be x cubed. So the degrees are equal. We do indeed have a horizontal asymptote, and it's going to be when y equals the ratio of these two leading terms. So if you were to FOIL it out, you'll see that I am indeed correct, and it's 1 over 1, which is 1. Now we can find our intercepts. So we've got our x-intercepts occurring when the function value goes to 0, meaning we're looking where that numerator zeroes out. So we got x-intercepts at 1, 0, at -3, 0, right, for that middle term, and then at the end at 5, 0. For the y-intercepts, we just plug in 0 for x, so we get -1 times 3, which is -3, times -5 is +15, over 0 plus 2 is 2, squared is 4, times -4 is -16. So we have a y-intercept of 0, -15 over 16, really close to -1. So once we get to this point, there's only one other thing we have to check, and that's check to see if this graph ever crosses that horizontal asymptote. You're not going to be crossing the vertical asymptotes. That's not going to happen, but sometimes you can cross the horizontal asymptote at certain points. So we're just going to check to see if there's any points where that does indeed happen. So the way we'll do that is we'll set the function equal to that value of the horizontal asymptote, which is 1. So once we have this set up, we can multiply out the denominator to the left side against 1. And then I'm going to kind of jump through the foiling steps just to spare you of like x plus 2 squared and then that times x minus 4. So I'm just going to FOIL it all out and run through and jump ahead, and then we're going to take it from there. So now we got it simplified out, right? For the denominator, when we multiplied across, we first got this, then we distributed the x minus 4, and we're left with this. And then down here, for the numerator, once you FOIL it out, you first get this intermediary step, and then we get this. So it's basically this polynomial is now set equal to this polynomial. So we can simplify that out. First, the x cubes cancel out. And then if we move everything to the right side, right, we add 3x squared to the right side. We add 13x to -12x, which is x, and then we subtract 15 from -16, we get -31, and this equals 0. And now we can try and factor, but it's not factorable, so in that case, we can run it through the quadratic formula to find these intersection points, theoretically, with the horizontal asymptote. So if we got a, b, and c like that, we've got -b, which is -1, plus or minus the square root of b squared. -1 squared, or sorry, 1 squared, excuse me, is 1 minus 4 times a, which is 3, times c, which is -31. Let's see if we can fit that in there. All over 2 times a, 2 times 3, which is 6. So this is not going to evaluate perfectly, so we're going to plug this into a calculator and get a nice approximation. So as we plug both of these in, we see that it's going to hit the horizontal asymptote at these 2 points, 3.05 positive and -3.38. And these are approximations, so now let's use that information. So these 2 points are right here, right? 3.05, 1, and -3.39, 1, and now we got enough to graph it. Let's do it. So first I'm going to start with the vertical asymptotes. We have one at x equals -2 coming straight down. We have another one at x equals +4 coming straight down. Those are the vertical asymptotes, hence vertical lines. Then we got a horizontal asymptote at y equals 1, like so. So that looks pretty good. And now we also have some intercepts here, right? We have x-intercepts at 1, 0, at -3, 0, which is right here, and then again at 5, 0. And then we also have a y-intercept at 0, -15, 16, which is really close to -1, so we could say like roughly there. Then we've got these interesting points where we intersect the horizontal asymptote or pass through it. So we got 3.05, which is right around here. Let's say it goes right there. And then we've also got -3.391, so -3.39 might be like here. So this right here is definitely plenty to get us going. So on the outer reaches, I don't see any crossing of the asymptote here, which means now we can just hug those asymptotes and draw it down, boom, and draw it up and kind of approaches it, but never crosses it. Then in here, we see that we have a cross, but only one cross right here. And we can definitely see that the behavior to the left is just going down, down, down. So then we'll follow through and hug that asymptote, and then we're going to continue up because it's crossing it, but it's not crossing back. So we know it's going to look like that in the middle. And then last but not least, we can see that This is obviously going down as we approach this asymptote, so we're going to hug that. And then we're coming up and we're crossing. Now, you might say, well, how do we know it doesn't go up here? Well, because that horizontal asymptote really dictates the end behavior, which means even though it's going to cross through, it's going to come back down and it's still going to follow along and be really, really close to 1, get closer and closer. So that's how you graph it. Boom, done. So for this one, it starts off by giving us these nice vertical asymptotes, some x-intercepts, and then a y-intercept. So we can use all of this to kind of piece this function together. So I'm going to start with the vertical asymptotes. And remember, vertical asymptotes are what's going to make that denominator go to 0. So if 5 is 1, I know I'm going to have x minus 5. And then if negative 5 is 1, I'm going to have x minus negative 5, aka x plus 5. Okay, and then for the x-intercepts, that's going to be what zeroes out the numerator. So if I have 2 as an x-intercept, then I'm going to have x minus 2 on the top, as well as x minus negative 1, aka x plus 1. Now, this is almost sufficient right here, except for we have to account for the fact that when we plug in 0 for x, we're getting 4. So there's some other multiplier here that we still don't know yet. So to find out that value of a, we got to plug in this y-intercept and solve for a. So when y equals 4, x is 0, which means we have on top 0 minus 2, which is negative 2, 0 plus 1, which is 1, over 0 minus 5, which is negative 5, 0 plus 5, which is 5. And then we get negative 2 over negative 25, which is just 2 over 25. And then to solve for this, we multiply by the reciprocal, 25 over 2, boom, boom, like so. 4 times 25 is 100, divided by 2 is 50. So a equals 50. So last step, we're going to rewrite everything with that nice a value of 50 in here. And then I'm going to simplify by foiling the numerator and the denominator, really only because the back of the book does it. Now, it's kind of up to your teacher. Maybe your teacher doesn't want you to do that. So check with your teacher, but I'm going to show you if we do foil it, it's x squared, and then you have plus x minus 2x, which is minus x, and then negative 2 times 1 is negative 2. On the bottom, this is a nice difference of squares. You might recognize it's a minus 5 and a plus 5, so it's going to be x squared minus 25. That's the shortcut, but you can foil it just to double check. Boom, done. For this one, we're going to start with these vertical asymptotes, and those are going to indicate where we're going to zero out for that denominator. So if we have negative 4, it's going to be x minus negative 4, aka x plus 4 on the bottom. That's going to give me, likewise, x plus 5. For the x-intercepts, that means the numerator is going to zero out at 4, so we need x minus 4. And for that negative 6, x minus negative 6, aka x plus 6. And then again, we have this horizontal asymptote at y equals 7. So what does that mean? That means that as we go right and left, we're approaching this value of 7, which really means that the degree on the top and the bottom are going to be identical, which right now they are, and the ratio of the leading coefficients is going to be 7 over 1. Well, right now, if I were to FOIL this out, you know I'd just get x squared and then other stuff, and then down here, x squared and other stuff. So all I need is to multiply that top x squared by a 7, and we're in business. We got that correct horizontal asymptote. So now all I'm going to do is I'm going to say y equals, I'm going to keep that 7 in the front, then I'm going to FOIL out the top and the bottom, just because, again, they do that in the back of the book, so we'll stay consistent. So we got x squared plus 6 minus 4, which is plus 2x, and then negative 4 times 6 is negative 24, over, we get x squared, and then 5x and 4x, as we're foiling, add together to get 9x, and then plus 4 times 5, which is 20. There's your answer, done. Here we're going to start with the vertical asymptote on the bottom right. That negative 1 is going to zero out the denominator, so we need x minus negative 1, which is the same as x plus 1 on the bottom. Then it says we have a double zero at x equals 2. A double zero meaning a multiplicity of 2 zeros. So normally I just have a typical x minus 2 on the top, but since it's a double zero, we have to square it. Last but not least, we know that the y-intercept is at 0, 2. So if there's a coefficient or an a value over here, we need to solve for that based on this point. So what I'm going to do is I'm going to plug 2 in for y, that's the y value, when x equals 0. So 0 minus 2 is negative 2 squared is 4, over 0 plus 1, which is just 1. So 2 equals a times 4 over 1, or 4a. So if 2 equals 4a, if we divide by 4, we get a equals to 2 over 4, which is 1/2. So now as I write this back in with a equaling 1/2, we've got a 1/2 in the front, and then we'll FOIL out that numerator. X minus 2 squared is x squared, and then you imagine it right as x minus 2 times x minus 2, and then it's negative 2x, which is negative 4x, and then negative 2 times negative 2 is positive 4, over that denominator of x plus 1. There you go. Here's the answer. Boom, done. So for this one, I'm going to start again with the vertical asymptotes, and we've got a vertical asymptote at 4 and negative 3. So that means I'm going to have x minus negative 3, aka x plus 3 on the denominator, and x minus 4 as well, and that's going to give us those nice vertical asymptotes. In terms of the x-intercepts, it looks like we only have one at positive 3, so I'm going to have x minus 3 on top, right? Then we plug in 3 here, and it's going to zero it out. And then the only thing I haven't accounted for is that y-intercept, meaning when I plug 0 in for x, I should get 1 for y. So we know that there's some missing a value potentially that we have to solve for, and we can solve for that by plugging in that y-intercept of 0, 1. So when I plug in 1 for y, I'm plugging 0 in for x. So on top I have 0 minus 3, which is negative 3, over 0 plus 3 is 3, 0 minus 4 is negative 4. So you'll see that we can even cancel those 3's out. I have negative 1 over negative 4, so I have 1 equals a times 1/4. Multiply both sides by 4, a equals 4, which means if I finalize this equation, I now have y equals 4 in the front. On the top, I got that x minus 3. On the bottom, I'm going to FOIL this just because they do so in the back of the book. Again, it's up to your teacher. But we have x times x, which is x squared. Then we have negative 4x, positive 3x, which is minus x. And then we have 3 times negative 4, which is negative 12. So there's your answer. Boom, done. For this one, we're going to start with the vertical asymptote. Since I have one at negative 3 and positive 3, that's going to serve as the start for our denominators. We have x minus negative 3, aka x plus 3. This one would be x minus positive 3, or just x minus 3. And then for the numerator, we're going to do that based on that nice x-intercept there of x minus 2. Okay, and the other thing I'll say is on this asymptote, you see how it's kind of like mirrored, right? It's going up on both sides. That's an indication that we have a multiplicity of 2 on that x minus 3. So this is actually going to be squared, okay? And now the last thing we have to consider is this y-intercept, meaning there could be an a value here that's going to get us that nice value of 0, negative 2. To figure out what a is, we're going to plug and chug. So we got negative 2 for y equals, plug in 0 for x. We got negative 2 on top, still the a in front, over, and then on the bottom we have 0 plus 3, which is 3, times 0 minus 3, which is negative 3, but that squared is 9. So then we have negative 2 equals a times negative 2 over 27. Multiply both sides by the reciprocal, which is 27 over negative 2. Negative 2's are going to cancel out, and a equals 27. This gives us our final answer of y equals 27 times that numerator of x minus 2 over x plus 3 times x minus 3 and squared. And there's your answer. Now, in previous answers, I FOILed this out because that's what they did in the back of the book. Here, the back of the book, they left it like this. So we're not gonna go any further. Again, it's up to your teacher if they want you to FOIL this and simplify this further. But this is a perfectly acceptable answer. Boom, done. So this one's pretty interesting because we have this nice vertical asymptote, but you can also see that we have this slant asymptote. Okay, so let's see how we can piece this together. First, I'm going to say that we've got a denominator of x minus 1. That's because we have that vertical asymptote. Now, the slant asymptote is interesting because right off the bat, it does tell me that the degree on the top has to be bigger. And that kind of makes sense because we also have two x-intercepts. So just piecing it together from the x-intercepts, we know that on top we need x minus negative 3, aka x plus 3, because it's going to need to be a binomial that's going to zero out from that negative 3 on the top. Likewise, we need x minus 2 over here. So this kind of satisfies the fact that we have a higher degree on the top, which justifies that slant asymptote. And then we have some unknown constant in front that we need to figure out what that is. And we can figure that out using this nice y-intercept of 0, 2. So we're going to plug and chug. Plug 2 in for y. And as we plug 0 in for x, we get 3 times negative 2, which is negative 6 on top, over 0 minus 1, which is negative 1, which means that is just a times 6. Divide both sides by 6. A equals 2 over 6, which is 1/3. So then as we write this out, finally, we get y equals 1 over 3, and then we get times, I'll put this in parentheses just to make it clear, and then they actually foiled it out in the answer. So you could leave it like this if your teacher says it's okay, but I'm going to foil it out like they did. So then we have x times x, which is x squared. Then we have negative 2x, positive 3x, which is just plus x, and then 3 times negative 2, which is negative 6, over that x minus 1. There's your answer. Boom, done. For this one, we're going to start with those nice vertical asymptotes at negative 3 and 2. So we know that in our denominator, we're going to start with x minus negative 3, aka x plus 3. And then over here, x minus positive 2, or just x minus 2. So we got that. And then we also want to look at that x-intercept for the numerator, which is occurring at 1. So we're going to have x minus 1 on top. But you notice that it's indicating that it's bouncing, okay? So it's not penetrating and going through, meaning this should have an even multiplicity. But let's just stick with a nice multiplicity of the lowest even number, which is 2. So now we have this, and then the last thing we have to factor in is that y-intercept. I don't know where that's exactly occurring. And then one other thing we need to consider is, again, look at this that is going down and down around this asymptote. When you see that nice mirroring, it's going down and down, versus here it's like up and down, right? When you see that mirroring, it indicates that this asymptote has a multiplicity of 2, or an even multiplicity, but let's just go with 2. So we also need a square over here. Now, the last thing is we need to figure out if there's a constant or an a value over here that we need to solve for. So we have one other point. Now, it doesn't say exactly, but I'm going to assume that our y-intercept here is 0, negative 1/2 for y. So we're going to plug in and see if we can solve for a. So I got negative 1/2 for y equals a times, and then we plug in 0. 0 minus 1 is negative 1 squared. It's just 1 over 0 plus 3 is 3 times 0 minus 2, which is negative 2 squared, which is positive 4. So we get negative 1/2 equals a times 1/12. And then, so to solve for a, we multiply both sides by the reciprocal of 1/12, which is 12. 12 times negative 1/2 is negative 6. And now for our final equation, we get y equals negative 6 out front. And then inside, we're not going to FOIL this out because they didn't in the back of the book. We'll leave it like this. And again, that's a teacher preference, whether your teacher wants to FOIL it or leave it like this. But I definitely think leaving it like this is great. So then we have x plus 3. And then we have x minus 2, again, squared, boom, done. So for this question, we're asked to make tables to show the behavior of the function near the vertical asymptotes and the, showing what's happening for the horizontal asymptote. And remember, horizontal asymptote is really end behavior. So what I did is I'm taking the exact same values they did in the back of the book, and I'm going to show you kind of why this works. So first of all, why did they choose these values that are really close to 2? Because the vertical asymptote is going to occur where the denominator zeroes out, which is when x equals 2. So we're doing values, we're getting values that get closer and closer to 2 on both the left and the right side. We're seeing what the behavior is as we go towards both of those places. So as we plug in 2.01, we're going to get 100. As we plug in 2.001, we actually get 1,000. And then 2.0001, you notice the pattern, we get 10,000, right? You could plug it in your calculator to double check. When we plug in 1.99, we actually get negative 100. And here we get negative 1,000. So you can kind of see that as you're approaching this vertical asymptote from the right-hand side, it seems to be going up and up and up. As we're approaching it from the left-hand side, we seem to be going down, down, down towards negative infinity. So that shows us that we do indeed have a nice vertical asymptote here at x equals 2. Now, what about end behavior? End behavior is going to be aligned with that horizontal asymptote, whatever we determine that to be, as we go really far to the right. Now, ideally, you want to also show it going really, really far to the left, right? Like negative 10, negative 100, negative 1,000. It will also show the same thing, that the values are getting close to that horizontal asymptote. But I'm just letting you know, this is what they have in the back, so we're going to roll with that. Now, the thing is, you see that the degree on the bottom is bigger than the top, that we have a 0 degree and we have 1 degree on the bottom. So when that happens, you know that the horizontal asymptote is y equals 0. So what we should see is as we get farther and farther out towards positive infinity, we should be approaching 0. And you'll see that when you plug in 10, you get 0.125. then you're going to get 0.0102. This is just an approximation. You plug in 1,000 in the calculator, you're going to get 0.001, 10,000, 0.001, and so on and so forth. So you see, what is it definitely approaching? It looks like it's getting closer and closer to 0. So we verified the horizontal asymptote, we verified the vertical asymptote, boom, done. So for this one, we're going to start by identifying our vertical asymptote, which is what value of x is going to zero out that denominator, which is going to be x equals -4. So there's our vertical asymptote, and this table is values all around -4, right? What happens if we get closer and closer to -4? And then for the horizontal asymptote, since the degrees are equal, both first degrees on the top and bottom, we're going to take the coefficients of those leading terms, which is 2x, right, over 1x, so 2 over 1. So the horizontal asymptote should be at y equals 2. And so let's first go to this first table, and we're going to plug in these values, -4.1, -4.01. Let's see where we're getting closer to as we get closer and closer to -4. So we've got 82 here. Next, we've got 802. Next, we've got 8,002. It sure looks like it's going up and up and up towards positive infinity. So that verifies that we do look like have in asymptote here, a vertical asymptote. And then as we get closer from the other side, right, from things that are just barely bigger than -4 but getting closer, we've got -798, then we've got -7998, getting closer and closer to negative infinity. So it looks like from the left side we're going up and up and up. From the right side, as we get closer to -4, we're going down, down, down. So there would be our vertical asymptote at -4. And then now we can see the end behavior if this coincides with our horizontal asymptote, meaning these values should be getting closer and closer to 2. So first we've got 1.4286 approximately, then we've got 1.9331, then we've got 1.992, then we got 1.9992, and then we got 1.99999. Again, you can do this all in a calculator or Desmos too, but look, that verifies what we were predicting, that end behavior, aka the horizontal asymptote, is indeed at 2, y equals 2. And this is indeed a vertical asymptote. We're going towards positive infinity from one side, negative infinity from the other. So that's how you do it. Done. So for this one, before we begin, we've got to figure out where that vertical asymptote is occurring. And in order to do that, I need to factor that denominator. So this is actually a nice perfect square trinomial if you recognize it. It's x plus 1 times x plus 1, right? That gives you x squared, 1x, 1x, that's 2x, and then 1 at the end. So what this means is that we have a vertical asymptote at x equals -1. And because it's squared like this, right, it's really x plus 1 squared. It has a multiplicity of 2. So what we should be seeing is we should either be seeing at that asymptote either both going up and up, or it should be going both down and down. So we'll see whether it goes on both sides, whether it goes to negative infinity or positive infinity. So we're going to check by plugging in values closer and closer to -1 from both sides. So here we would get positive 81, then 9,801. Again, I'm just plugging this value in for x and evaluating in a calculator. Then here we'd get 998,001. Sure, seems like we're going up and up, right, towards positive infinity. So this should probably yield a similar result. So let's check it out. -1.1, we're going positive 121. Here we're going 10,201. Sure seems like it's going up. So that's a nice verification that we've got our vertical asymptote identified correctly at x equals -1. Now for end behavior, since the degrees are the same at the top and the bottom, we're going to take the coefficients of those x squared terms, which is 1 over 1, meaning we should have a horizontal asymptote, aka end behavior, at y equals 1. So let's verify. Let's see what happens as x gets really, really big. So first when I plug in 10, I get roughly 0.826. Then I get 0.9803 when we plug in 100. So as we're getting bigger and bigger, now I'm getting 0.998, then 0.9998. We're getting 0.99998. Well, what does it definitely look like it's approaching? It looks like it's approaching that nice value of 1. So there we have it. Horizontal asymptote here, vertical asymptote here. Boom, done. So for this one, we're meant to graph it and figure out when the function value is greater than 0. So let's do that now in Desmos. So here, as we look at the graph, we look like we have a vertical asymptote somewhere roughly at 1.5. And it looks like, and we can verify that with the vertical asymptote. If you plug in 1.5 here, you'll zero out the denominator. So it looks like to the left, it's all negative, but to the right, everything's positive, right? So I would say for all values greater than 3/2, aka 1.5, And if we put that in interval notation, it's everything from 3/2 or 1.5 to infinity. And we're not including, it's not a square bracket because we're not including 3/2 because, again, it's a vertical asymptote. It actually doesn't exist at 3/2. But this is your answer. Done. So for this one, we're meant to see where f of x is greater than 0, and we're meant to do it by looking at the graph, so we're going to graph it in Desmos now. So here it sure looks like the horizontal asymptote is 0, which we can kind of tell here, right? And we can also see from the graph that it does appear to cross that horizontal asymptote, right here at -2 and then stay below. So if we're looking for where it's positive, appears to be positive up to this first vertical asymptote, which appears to be at 1, which we can verify here. So I'd say everything from -2 up to 1, not including 1 and not including -2 because we're trying to be greater than 0. And then we pick it up again on the other side of this vertical asymptote at 4, and that is going to continue forever because it doesn't look like it ever crosses that horizontal asymptote, so it's always going to be positive for the remainder. So just to summarize, we're going from -2 up to +1, and we don't include it because that's a vertical asymptote. And then we join it with everything starting at 4 but not including 4 again because that's another vertical asymptote going out to infinity. There's your answer. Done. For this question, we're meant to identify the removable discontinuity, and to do that, we have to start by factoring the numerator and denominator. So the top is a difference of squares, x - 2 times x + 2, and that bottom is, you can't do anything with it, right? It's just x - 2. And then we can see if we can cancel anything out, which we can. We can cancel out the x - 2, and we're left with just x + 2 for the simplified function. So we know then that the whole occurs at whatever was going to zero out those canceled out binomials. So I know my whole is going to occur, or removable discontinuity, you can also say, is going to occur at 2. But 2 comma what? Well, to figure that out, we plug this 2 back into the simplified version, and we get 2 + 2, which is 4. So here's my removable discontinuity at 2 comma 4. Boom, done. In order to find a removable discontinuity, we're going to have to start by factoring both the top and the bottom. So the bottom doesn't factor because it's just a binomial x - 2. But the top, we're trying to figure out what two numbers multiply to -6 and add to 1. That's +3 and -2. Then we see that we can cancel something out, which is x - 2. So that goes away, and we're left with a simplified version of the function at x + 3. Now, the x - 2 that we canceled out, that's where this removable discontinuity will occur in terms of x. You know, what's going to zero out those two binomials, and that's going to occur at +2. And then where's the corresponding function value? Well, to figure that out, you got to plug it into the simplified version, which is 2 + 3, which is 5. So there's your removable discontinuity. It's occurring at 2, 5. Boom, done. So for this question, we have to start by factoring the numerator. We can factor out a GCF of x squared, and then we have x and 1 left inside, right? If you redistributed it, you'd get x cubed plus x squared. So that's how you can verify it. And then on the denominator, we got that nice x + 1. Now we can simplify because I got x + 1 on the top and the bottom, and they cancel out. And we're left with a simplified version of x squared. And that means the removable discontinuity occurs when x is going to zero out that binomial that we canceled out, which means it's going to occur at -1. And -1 what? Well, to figure that out, you take that and you plug it into the simplified function, which is x squared. So -1 squared is +1. So there's your removable discontinuity, -1, 1, boom, done. In a refugee camp hospital, a large mixing tank currently contains 300 gallons of water, into which 8 pounds of sugar have been mixed. A tap will open, pouring 20 gallons of water per minute into the tank. At the same time, sugar is poured into the tank at a rate of 2 pounds per minute. Find the concentration pounds per gallon. So it's literally pounds divided by gallons. So we're starting off with 8 pounds of sugar divided by 300 pounds of water. And then the sugar and the water is increasing simultaneously. So the sugar on top, right, we're starting with 8 pounds, is increasing at 2 pounds per minute, where t is minutes. And then the water is increasing at 20 gallons per minute, right, also per minute. So 300 plus 20t per minute. And this gives us that concentration. This will give us the total pounds over the total gallons. And then we can represent this as concentration, aka C, as a function of time. There's your answer. Done. So this says the concentration of a drug in a patient's bloodstream is given by this. And it says use a calculator to approximate the time when the concentration is highest. So what I'm going to do here is I'm going to actually plug this into Desmos and look at the graph. I'm going to look for some sort of a maximum. So here what I did is I plugged it in as x instead of t because we wanted to graph it on this xy coordinate. And we're looking for a max. Well, I do see a min right here. That's a local min, but also an absolute min, meaning it's the lowest point of the function. And here is where I see that nice max. So the max is occurring here when time equals 6.124, and that's what it's asking. It's asking for the time at which the max occurs, and the max is that value. So we would say the concentration is highest at 6.12 hours. Boom, done. So for this one, we have a rectangular box with a square base is to have a volume of 20 cubic feet. So now we got the bases are 30 cents, the sides, which are all these four sides, and the outside are 10 cents, and the top is 20 cents. And now what about this height, right? How do we represent this height? Well, using the formula for volume, which equals, length times width times height, we can say the volume of 20 equals length times width, which is also x, times height. We can get an expression for height, which is 20 divided by x times x, or 20 divided by x squared. Now we have enough information to come up with a nice cost function with all this information. So we have cost equal to the base, which is the bottom, which is x times x, that's squared. And it said it's 30 cents per square foot. So if I do this in cents, I can say 30 times x squared plus, and then the top is also x squared, right? It's also going to be the same. Xx is going to be a square box, and that's going to be 20 cents. And then now we get the sides, which is going to be the areas is x times 20 over x squared, x times 20 over x squared. And that's one of the sides. And then there's four of those. And then each one of these costs 10 cents. So then we're also going to throw a 10 in front. So as we further simplify, we got c equals 30 plus 20, which is 50 x squared. Again, this is in cents, not dollars. So just keep that in mind. And then here we have 40 times 20, which is 800 over, and then the x and the x squared cancel out to just be an x on the denominator. So now we're trying to minimize the cost. So what I'm going to do is I'm going to graph this function in Desmos. We're going to look for a minimum. So as we kind of graph this, we see that our minimum, a realistic minimum, because these values over here don't really count because they're in negative x values. We can't have negative dimensions. It wouldn't make sense for a geometric figure. But once we're in the positive domain, we see here these give all these different costs. And look at that. We want that minimum, which is occurring right there at a cost of 600, but more importantly, the dimension for x is 2. So if x is 2, we know that the base, we could say it's a width of 2, a length of 2, and then a height of plug in 2 here, 20 over 2 squared. 2 squared is 4, 20 over 4 is 5. So we have a width of 2 feet, a length of 2 feet, and a height of 5 feet. Boom, done. A right circular cylinder with no top has a volume of 50 cubic meters. So let's draw that out. Find the radius that will yield the minimum surface area. So x is our radius. We don't know the height, but we can come up with an expression based on the volume. Because we know that volume of a cylinder, 50 in this case, equals pi times radius squared times the height, which means that the height, if we divide by pi x squared, the height is 50 over pi x squared. So now we have a representation for height as well. And now if we're trying to find the minimum surface area, we need to write an expression for the surface area. So the surface area of a cylinder is the area of the bases. But again, the top is open, so we only want one of the bases, meaning the circle at the bottom, which is pi r, which in this case is x, pi times the radius squared. And just one of them, normally it'd be 2, but it said nothing on the top, plus the lateral surface area, which is like the circumference of the top part, which is 2 pi x, and then it's that circumference times the height, but we already know the height is 50 over pi x squared. And then as we simplify this, we get pi x squared plus that cancels with one of them, and then 2 times 50 is 100 over x. So now we have a nice function, and we can say equals there, and then we can graph this, and we're going to look for a minimum surface area. So again, here's our graph. We're not concerned with the negative values because we're not talking about negative radii. That wouldn't make sense in this case, but here we do have that nice minimum. Look at that. It's occurring when x equals 2.515 rounded up to 2.52. And again, x represents the radius. So to get that minimum surface area, we need a radius of 2.52. So the answer is 2.52, And we're talking about meters because we're in cubic meters. So just regular meters, boom, done. I hope you guys enjoyed this video. And if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.